Greetings. I want to talk about this function with you right now. And what the thing about it I'd like to talk about is not computing limits on it directly. What I want to do with you is find the derivative at some point A. I'm going to find the derivative at some point A. So but I'm not going to give A a concrete value. I'm just going to leave it as a placeholder. And the nice thing about leaving A as a placeholder is that later if I want to figure out what it is at some specific A, then boom, all I have to do is replace A with my specific number and I have it. So let's start from the definition of the derivative. And the notation that we use for derivative is f prime. F prime at A. That's the derivative at A. Another word for the derivative is the instantaneous rate of change, or the slope of the tangent line. Those are words for the same thing. Is given by this limit. The limit as h approaches 0 of a ratio of two things. We call this the difference quotient. So f at A plus h minus f at A divided by A plus h minus A. I wrote it in this form here so that you can see that it really is like delta f over delta x. So if I simplify that thing, so let's just do that straight away. And I'm going to do that not by writing a whole new line for it, because I just don't have that much space on this board. So I'm just going to do this difference. I'm going to drop my parentheses. And then I'm going to be like, well, I have A and minus A. And those two things go out to play in the park with each other. And we're left with just H. So we have just H. So another way that you'll see the difference quotient written is just like this. So we have a difference in function values and then a difference in x values that we've just omitted like the x part for you. Let's go and make this explicit now by substituting in the f that we have, and then in place of x, we're going to put a plus h and a. Okay. So this whole thing is equal to the limit as h approaches 0 of f, which is 2 over the quantity 8. And now in place of x, I have a plus h plus 5 minus 2 over 8. Oh, I don't need parentheses there. A plus 5 divided by h. And now I need to simplify. So I think as far as simplification goes on this, the right thing to do is to do a common denominator. Yeah, I think the right thing to do is to do a common denominator. So let's do that. So, and I might have to wander up here and then stand behind this for a little while in case the, well, how hard is it to erase? Yeah, we'll see. So let's do common denominator. So this is lim h approaches 0, 1 over h times, so I need to multiply this one by 8a plus 5 over 8a plus 5. So I have 2 times 8a plus 5 divided by 8 times a plus h plus 5 minus times, because of the common thing, 8a plus 5 Ooh, I'm just gonna go ahead and combine them now because I'm not gonna have enough room. So now I'm gonna have minus 2 times this thing right here. So that's 2 times 8a plus h plus 5. You know what I vote? I vote we take that 2 out. Because I do not want to have to deal with that 2 hanging out. Ooh, I love the constant product rule because it let me just pull multiplicative constants out front. How's our friend the constant product rule at force there? So now we need to do some distribution. And so we've got 8a plus 5 right here. Let's distribute this 8 across this quantity right here. And I'm going to go ahead and do that in line 2 before my line starts getting too long here. So 8 times across that thing. I'm just going to move that paren to the left a little bit. So I have 8a plus h is the same as 8a plus 8h. All right. And now let's distribute this minus sign across this quantity. So I'm going to drop my parens to do the distribution. And I'm going to get a minus sign right there and there. So I've got a minus and a minus. Hey, things are working pretty good for us. I'm going to drop these parens over here. They cease to be useful. Okay, hey, check this out. Check this out. This 8a, look, there's a minus 8a right there. So those are paired up. So shwick, shwick. And that's taking that one out. Ooh, I've got a 5 and a minus 5 right there. And we already did the minus distribution, so I'm left with just minus 8h on the top. And then in the bottom, I still have this mess. But, oh, do you see what I see? Look right here. I've got an h hanging out in the denominator. I've got an h hanging out right here, divided by h, 1 over h. And look, I've got an h right there. Oh, this is so fortunate. I just love this. This is great because when I have an h up top and an h down in the bottom and a thing like this, I can be like, well, we're just going to take that h and let those cancel each to be 1. And that is super nice. And I'm left over with this minus 8 right here. So I think I'm going to risk going even further on the bottom of the screen here and write this as 2 times the limit as h approaches 0 of minus 8 over this whole mess right here. And there's no way that I'm foiling that out. There's no way that I'm foiling that out. So 8a plus h plus 5 times 8a plus 5. All right, so we've got a limit. We've been studying limits all semester. We know how to do limits. Or we're working on it at least. It's okay if you're still working on that. It's always work in progress, mathematics is. So, in some sense, like up here, we just wanted to be like, well, let's just plug in h and see what happens being 0. So I'd have like 0, I'd have this thing and this thing, it would just cancel and I get 0 over 0 indeterminate form, and I'm like dead in the water. Except that we know how to deal with indeterminate forms. We've been spending all that time dealing with indeterminate forms. So that's why we're like, well, we'll just bust out our algebra skills, engage in this thing right here, and lo and behold, I end up with something simpler. And every time we've done an algebraic simplification, we should try to substitute. So let's see what happens if we substitute. I've got h, and that's the only one that's left. So h, that's going to go to 0. Everything else is going to be all good. So, I think that we're golden to just go ahead and write down and we get an expression. So let's just evaluate that limit. So this thing right here, once we do the limit, like we're done writing the limit. So I'm going to get 2. Spacing is going to be unpredictable on this one. So I'm going to get 2 of, I have minus 8. Should we just moosh 2 and minus 8 together and call that minus 16? Are you down? Can we do that? I think we should do that. So we've got minus 16, and then that's over. And look, if h goes away, I just have 8a plus 5. 8a plus 5. That's 8a plus 5 squared. 8a plus 5 squared. Nice. And that's the derivative at a, the slope of the tangent line. A is just a placeholder. So now if you just want to like plug in some a's and figure out what that slope of the tangent line, you can totally do it. And it'll match any other method of computing the slope of the tangent line, including the stuff that we did at the very beginning of class when we were playing with instantaneous rates of change and average rates of change and slopes of secant lines. So that's the general process. I kind of feel like this was like an inverse linear function. And in general, when you compute limits like this, this is going to be the pattern. We do the difference quotient. And we just got like difference in function values upstairs. One of them is perturbed by h. Or like you'll often see like delta x or delta t is another name for people that people use for h. Some people like h because it's just one symbol. It's all good with me. You can call it whatever you want. Delta x, delta t, and h are the most common ones. So I've got this difference in function values, and then I divide it by h. You're going to do some algebra, and h is going to cancel when you do one of these derivatives. H is going to cancel. I promise you there's a way to make h cancel. If you're doing some big nasty function, it probably requires some algebraic tricks or something like really slick to find the way to do it. But for like polynomials and inverse functions like this, like reciprocal functions, it's all good. So yeah, that's the derivative by definition, and I'm pretty happy with it. So thanks for watching, and I hope you have a lovely rest of your day, whatever you got to. Bye.